Hello everyone, and welcome to today's presentation. I'm excited to have you here as we explore the key parameters in wastewater treatment. The focus of our discussion is on MLSS versus MLVSS, and how understanding these metrics can drive efficient biological treatment and operational excellence in activated sludge systems. Over the next few slides, we'll cover what these parameters are, why they matter, and how they impact your treatment processes. So let's get started. So what exactly is MLSS? Well, MLSS stands for Mixed Liquor Suspended Solids, and it essentially measures the total amount of suspended solids in the aeration tank's mixed liquor. This includes both organic and inorganic components, giving us a comprehensive picture of what's present. When we talk about these components, it's important to understand that it includes active microorganisms and bacteria that are doing the work of breaking down waste. It also encompasses biodegradable organic matter, which is the food source for those microbes. Plus, there are inert particles and mineral content, things that don't readily decompose. Another key element are extracellular polymeric substances, or EPS, which are substances secreted by microbes that help form biofilms and flocks. All of these together impact how effectively the treatment process works. Now, measuring MLSS involves a straightforward process. We take a sample, dry it at 105 degrees Celsius to remove all water, and then carefully weigh what's left. That weight gives us the total concentration of solids in the sample. Understanding MLSS is crucial because it helps us gauge the health and efficiency of our biological treatment process, ensuring everything is functioning as it should. So let's talk about what MLVSS actually is. MLVSS stands for Mixed Liquor Volatile Suspended Solids, and it specifically measures the organic, biodegradable part of the MLSS. This is crucial because it helps us understand the amount of active microbial biomass in our system. When we say active microbial biomass, we're referring to things like bacterial cells, extracellular polymeric substances, which are the sticky substances microbes produce, and some insoluble organics that are part of this organic matter. Now, how do we test for MLVSS? The process involves taking a dried sample of MLSS and heating it up to 550 degrees Celsius. This high temperature causes the volatile solids, meaning the organic, biodegradable parts, to combust or burn away, leaving behind only inorganic residue. This method gives us a clear picture of the organic content in our mixed liquor, which is vital for assessing the biological activity in our treatment process. Understanding MLVSS is key because it ties directly into how effectively our microbial communities are working, which ultimately impacts the overall efficiency of our wastewater treatment. Now, let's take a closer look at the core differences between MLSS and MLVSS. First, MLSS, or Mixed Liquor Suspended Solids, represents the total picture. It measures the complete solids concentration in the mixed liquor, including both biological solids and inert materials. Think of it as the overall concentration of everything suspended in your wastewater sample. On the other hand, MLVSS, or Mixed Liquor Volatile Suspended Solids, isolates the biologically active solids, that is, the microbes that actually perform the treatment process. These are the microorganisms responsible for breaking down organic matter and removing pollutants. A critical relationship to remember here is that MLSS is always greater than or equal to MLVSS. The ratio between these two gives us valuable insight into the system's health and efficiency. If the ratio is too high, it might indicate inert materials are dominating or microbial activity is low. Conversely, a healthy ratio suggests a good balance. The most important takeaway is that MLVSS reveals the microbial health and the actual biological activity happening in the system. That makes it a more valuable indicator when we're assessing how well our biological process is performing. So, while MLSS gives us a broad overview, MLVSS provides the specific insight into the biological activity driving the treatment's success. Now, let's talk about why MLSS and MLVSS are so important in our wastewater treatment process. Starting with MLSS applications, one key area is solids load monitoring. By tracking the total solids concentration, we can prevent system overloads that might compromise treatment efficiency. It's like keeping an eye on the system's workload to ensure everything runs smoothly. Next is sludge production. Monitoring MLSS helps us predict how much waste sludge will be generated and plan for its disposal accordingly. This way, we can manage costs and logistics effectively. Another critical aspect is settling behavior. Observing MLSS levels gives us insight into the clarifier's performance and helps identify potential bulking issues, which can cause poor settling and affect water quality. Moving on to MLVSS applications, these focus on the microbial population. Measuring active biomass tells us how many microbes are available to break down pollutants. It's essentially a health check for our biological treatment process. In terms of treatment efficiency, MLVSS helps us assess how well organic matter is being removed, giving us an indication of the system's overall health and performance. Lastly, MLVSS guides process optimization. By understanding the active biomass, we can make informed decisions about aeration rates, sludge wasting, and nutrient balancing to keep the system operating at peak efficiency. In essence, both MLSS and MLVSS are vital tools that help us monitor, control, and optimize our wastewater treatment processes, ensuring we meet environmental standards effectively. Let's take a closer look at the typical MLSS and MLVSS values you'll encounter in different activated sludge systems. Starting with conventional activated sludge, the MLSS range is generally between 2,000 and 5,000 milligrams per liter. These systems usually operate with moderate loading rates and rely on traditional settling processes. Now, moving to more advanced systems, like membrane bioreactors or MBRs, the MLSS range is much higher, typically between 8,000 and 12,000 milligrams per liter. That's because MBR systems are designed to support higher biomass concentrations, which improves treatment efficiency and allows for smaller footprint systems. It's also important to understand the proportion of MLVSS, or mixed liquor volatile suspended solids, within the MLSS. Usually, MLVSS makes up about 60 to 80% of the total MLSS. However, this percentage can vary depending on the health and age of the system, as well as the characteristics of the influent wastewater. Overall, these values are key indicators of how well a system is functioning and help us tailor operational strategies to maintain optimal performance. Let's take a closer look at the operational implications of MLSS and MLVSS levels. Starting with low MLSS levels, one of the main risks is that we don't have enough biomass to effectively treat the wastewater. This can lead to poor pollutant removal, meaning contaminants might slip through the system. Additionally, when biomass is insufficient, the system struggles to handle load variations, which can cause process instability. On the other hand, high MLSS levels present their own challenges. Excessive sludge can cause bulking and poor settling, which hampers the clarity and efficiency of the process. It also increases energy consumption because more aeration is needed to keep everything moving smoothly. Ultimately, this translates into higher operational costs. Now, looking at low MLVSS levels, these are indicators of weak microbial activity. If the microbial population isn't active enough, organic material isn't broken down effectively, which affects treatment quality. It can also signal system stress or toxicity, suggesting that conditions might be unfavorable for microbial health. To manage all these issues effectively, monitoring best practices are essential. It's important to track trends over time consistently. That way, we can spot potential problems early. Using standardized testing methods ensures our data is reliable and comparable. And finally, documenting operational conditions thoroughly helps us understand what's influencing system performance and guides us in making informed adjustments. All these practices are vital for maintaining optimal biological treatment processes. All right, let's talk through how we can measure and calculate MLSS and MLVSS effectively. First, we need to collect a representative sample. This means taking a well-mixed liquor sample directly from the aeration tank during normal operation. It's important that the sample reflects the typical conditions inside the tank. Next, we move on to filtering and drying for MLSS. We filter a known volume of the sample through a pre-weighed filter, then dry it at 105 degrees Celsius until we reach a constant weight. This step allows us to determine the total suspended solids, including both organic and inorganic material. Now, to calculate the MLSS concentration, we use this formula. Take the dry weight minus the filter weight, multiply by 1,000 to convert grams to milligrams, and then divide by the sample volume in milliliters. This gives us the concentration in mg/L, which is a key indicator of the biomass in the system. The next step is to ignite the dried sample at 550 degrees Celsius for about 15 to 20 minutes. This process burns off the volatile organic matter, leaving behind inorganic residue. It's crucial because it helps us differentiate between organic and inorganic solids. To find the MLVSS, we subtract this remaining inorganic residue from the total MLSS. This gives us the volatile suspended solids, which are a good measure of the active microbial biomass. For example, if our MLSS is 2,060 mg/L and volatile solids make up about 70% of that, then our MLVSS would be approximately 1,442 mg/L. This high MLVSS value indicates that the microbial activity is healthy and robust, which is exactly what we want to see in a well-functioning treatment process. So, by following these steps, sampling, filtering, drying, igniting, and calculating, we can accurately assess the biological health of our system. It's all about understanding the microbial population and ensuring our process is working optimally. In this slide, I want to walk you through a real-world example of how we optimize treatment processes using an operational control strategy. First, we focus on RAS flow adjustment. Plant operators are constantly monitoring and adjusting the return-activated sludge flow rates to keep the mixed liquor suspended solids, or MLSS, within that optimal target range. Maintaining the right MLSS level is crucial for effective treatment. Next, we look at aeration rate tuning. By carefully fine-tuning the dissolved oxygen levels, we support a healthy and active microbial community. We use MLVSS measurements, mixed liquor volatile suspended solids, as an indicator to ensure that microbes are thriving and doing their job efficiently. Preventive monitoring is also a key part of this strategy. Regular testing of MLSS and MLVSS helps us prevent issues like sludge bulking, which can disrupt the process and affect effluent quality. By staying ahead of potential problems, we can maintain consistent standards. Looking at the numbers here, we aim to keep the MLSS around 2,800 mg/L for optimal performance. The MLVSS ratio, which shows the healthy biomass fraction, is maintained at about 75%. And through this balanced control approach, we're achieving about 98% BOD removal, which is a strong indicator of effective treatment. Overall, this example highlights how continuous adjustments and monitoring help us optimize the entire process, ensuring we meet our treatment goals efficiently and reliably. In conclusion, balancing MLSS and MLVSS is crucial for effective wastewater treatment. These two parameters work hand in hand as complementary indicators, helping us get a full picture of the biological process. By understanding their differences, operators can better optimize microbial health, manage solids effectively, and keep the treatment process running smoothly. Consistent testing and trend analysis of MLSS and MLVSS are key to maintaining sustainable performance over time. This approach supports not only environmental protection, but also the long-term efficiency of the system. From an economic perspective, mastering these parameters can lead to significant cost savings. It helps reduce operational expenses, cut down on energy use, and ensures we stay within regulatory requirements. Overall, by carefully balancing MLSS and MLVSS, we can achieve operational excellence, sustainability, and financial efficiency, all vital for successful wastewater treatment.